Hey guys, chapter 9, estimating values of a parameter. So this is section 9.1, estimating a population proportion. So we'll start with point estimate. So a point estimate is a value of a statistic that estimates the value of a parameter. So a point estimate could be relating to the mean, it could be related to the standard deviation, or it could be related to the proportion. So again, a point estimate X bar is going to be for the mean. A point estimate S would be for standard deviation for the population, standard deviation, population mean. And P hat is going to be related to the population proportion P. And so, for example, the point estimate for the population proportion is P hat, where X divided by N, or where P hat is X divided by N, where X is the number of individuals in the sample with the specified characteristic, and N is a sample size. So here we have an example of that. So the Gallup organization conducted a poll in which simple random sample of 1,015. So that tells us that N is equal to 1,015. Americans 18 years and older were asked, do you consider the amount of federal income you have to pay is too high? Of those 1,015 adult Americans, 458 said yes. So we have X is equal to 458. Obtain a point estimate for the proportion of Americans 18 years and older who believe the amount of federal income tax they pay is too high. So here we had 458 of them saying yes out of 100 or 1,015. So all we would have to do is N, and that's 1,015. X in this case is 458. So P hat, let's see if we have a P hat. Doesn't look like we have a P hat, so we could just use this for P hat. And P hat is going to be equal to 458 divided by 1,015. And that's our point estimate for population proportion. So again, that is our point estimate for population proportion. And we can write that down just so we have it here in our stuff. 0.45123, so 1, 2. And coming back over here, so obtain point estimate. So one more time, Gallup organization conducted a poll in which a simple random sample of 1,015 American 18-year-olds. So considering this right here, this is a sample that we're using. This obviously isn't a population because there's more than 1,015 American 18-year-olds. So this is our sample, and from our sample, we're creating our point estimate. So some information is good information. So even if you have the tiniest bit of information, you could still use that to make some sort of prediction about the population if everything was randomized and all that. So we have that, our point estimate of 458 divided by 1,015, and they just went out 3 decimal places. We went out 4. So we estimate the proportion of Americans 18 years and older who believe that the amount of federal income tax they have is too high to be 0.451 or 0.4512. Now, in statistics, we construct an interval for a population parameter based on a guess along with the level of confidence. So the guess is a point estimate of the population, and the level of confidence plays a role in the width of the interval. So here, notice that the interval, so the higher the confidence level, the bigger the interval. So again, higher confidence, if you're 100% confident, you want something that's extremely wide, right? So if we look at I don't know, just looking at a random picture of someone and guessing their age, you're always going to go extremely low and extremely high for a confidence interval of 100%. So us guessing the age of, I don't know, someone popular, we could say like Kim Kardashian. So Kim Kardashian has a lot of plastic surgery. So we're going to keep her age over here at 20 because we know that she's been on air for about 20 years. So minimum age would be about 20. Maximum age, she doesn't look that old. So we're going to say 60. We're 100% or we're 100% confident that Kim Kardashian is somewhere between 20 years old and 60 years old. As you lower that confidence, you're lowering the range. So if you say 99% confident, I would say something a little bit more realistic, maybe 30 over here. We know she's not 60, so we could say maybe 50 over here. And narrowing it down, the lower the confidence, the smaller the interval. So that's just what this is. Higher confidence makes a larger interval, lower confidence makes a smaller interval. A confidence interval for an unknown parameter consists of an interval of numbers based on a point estimate. So the level of confidence represents the expected proportion of the intervals that will contain the parameter if a large number of different samples is obtained. The level of confidence is denoted as 1 minus alpha times 100%. So 1 minus alpha, this is going to, we could say something along the lines of, if we're looking for just 5%, alpha being 5%, and what that would look like would be, actually, let's say 5% here and 5% here. So that would be a total of 10%. So here in the 90, we would, or in the middle, we would have that middle 90%. So here it would just be about 90%. Us looking at that 5%, adding those two 5% up because it makes up those left, the left area and the right area. And subtracting that from 100, we would get 90%. So that's all that we have there. Oh, and here we go. So for example, a 95% confidence level of confidence, alpha equals 0.05. So for a 95% level of confidence, alpha equaling 0.05 implies that if 100 different confidence intervals are constructed, each based on a different sample from the sample population, we would expect 95 of those intervals to contain the parameter and about 5 to not include the parameter. So review what we know about the model about the model that describes the sampling distribution of p hat, the sample proportion. So far we have the shape of the distribution of all possible sample proportions is approximately normal, provided that we have this right here. So n times p times 1 minus p. So n times, n times p times 1 minus p is greater than 10. And the sample size is no more than 5% of the population. So those are the two things that we have to look for in order to use this sampling distribution. And the data are obtained randomly. 2, the mean of the distribution of the sample proportion equals a population proportion. So that is that the mean of p hat is equal to p. And the standard deviation of the distribution of the sample proportions, also known as the standard error. So that is our standard deviation, or the standard deviation of p hat is equal to the square root of p times 1 minus p divided by n. So we have these two things identifying our spread. And because the distribution of the sample proportion is approximately normal, we know that 95% of all sample proportions will lie within 1.96 standard deviations of the population proportion. And we could get these numbers with Excel. So within 1.98 standard deviations of the population proportion, and 2.5% of the sample proportion will lie within each tail. So remember, this is 95%. And that means that we have 5% to share with this side over here and with this side over here. So half of 5% gives us that 2.5% that we see right here. All right, next, it is common to write confidence intervals or confidence interval estimates for the population proportion as our point estimate plus or minus our margin of error. So I don't remember them stating this part, but what we're doing is we're looking at our point estimate. So here we're looking at our point estimate for for proportion. So point estimate for proportion, we know that this area here, that the same distance to the left and the same distance to the right is going to make up the interval for what we believe P to be. And here that we have our point estimate, so that's what they're talking about here. So what we're doing is first subtracting our point estimate to get this area to the left of our point estimate. And the next thing we're going to do is add it to the right side, or to get the right area over here. And that area that we add and subtract, or that amount that we add or subtract, is going to be our margin of error. And the margin of error is actually computed. They should show us here in a few minutes. All right, so the margin of error for a 95% confidence interval for the population proportion is 1.96 times our standard deviation of the population proportion. So this determines the width of the interval. So I'm not sure if they give you this, but here, this is only for a 95% level of confidence. So let's simplify it and just say our critical value for our normal distribution times the standard deviation of our population proportion, which, if you remember in the previous slide, we have our critical value. Our standard deviation was the square root of P hat times 1 minus P hat divided by N. So this here is our margin of error. That's how much we're going to add and subtract to our point estimate to come up with our confidence interval. So to visually illustrate the idea of the confidence interval, draw the sampling distribution of P hat. Now create a slider that shows P hat 1 minus, or P hat minus 1.96 times our standard deviation. And this is what they're saying. So here, whenever P hat is here, it still catches our margin of error here and over here. But whenever P hat is not in this interval, whenever it's not in this shaded region of 95%, then it doesn't catch our population proportion. That's all this video, or that's all this picture is displaying. So the figure tells us that for a 95% confidence interval, 95% of the sample proportion will result in a confidence interval that includes a population proportion, while 5% of the sample proportion will result in a confidence interval that does not include the population proportion. So again, if we have 95% here, that means that we're sharing 5% with the left side and the right side. So half of 5% is 2.5% here and 2.5% here. So this means that our our population proportion is only going to not be within the intervals at 5%, or 5% of the time, or 5% of the samples that we test. So this is still a really great estimate. 95%, you're catching it correctly 95% of the time, but you're also leaving a little bit of it out. All right, so here illustrate what 95% confidence means on a 95% confidence interval in another way. All right, so simulate obtaining 200 different random samples of size n equaling 50 and a population p equaling 0.7. So the figure on the next slide shows the confidence intervals in groups of 100. A green interval is a 95% level of confidence, or 95% confidence interval that includes a population proportion with 0.7, and a red interval is a confidence interval that does not include the population proportion. So for now, ignore the blue intervals. Notice that the red intervals that do not capture the population proportion 0.7 have centers that are considered far away or more than 1.96 standard deviations or standard errors, standard deviations away from the population proportion or the sample proportion. And those are from 0.7. So of the 200 confidence intervals obtained, 10, the red intervals, do not include the population proportion. So let's see what they're talking about. Here, again, what we're looking at is whether or not the middle part is inside the level of confidence. So here we're pushing everything a little bit too far to the left, which didn't catch the 0.7. So I'm guessing that the estimate was a little bit too far to the left over here. For this one, for all of these other ones, it did catch it. So we could see that there aren't that many that weren't caught. 4, 5, 6, 7, 8, 9. And I don't see that last one. They said there were 10. This one right here. All right, so with all of these 10 different possibilities, or with all these 200 different possibilities of sample means or sample proportions, only 10 of them did not include the actual population proportion, which was 0.7. So this is just the exact same thing stated a little differently. For example, the first interval to miss had a sample proportion that was too small, that is too small to result in the interval that captures the 0.7. The second interval to miss has a sample proportion that is too large, the results in the interval to capture the 0.7. So 190 out of the 200, or you could think of that as 95%, they just divided those two numbers, of the samples have intervals that capture the population proportion. So again, we're still not really doing anything with like computing anything. This is just to show you a different way that we caught our population proportion, or we didn't catch our population proportion. So a 95% level of confidence means that 95% of all possible samples result in confidence intervals that include the parameter, and 5% of all possible samples result in confidence intervals that do not include the population parameter. Caution, a 95% confidence interval does not mean that there is a 95% probability that the interval contains the parameters, such as p or mu. Remember, the probability describes the likelihood of an undetermined event. Therefore, it does not make sense to talk about the probability that the interval contains a parameter, since a parameter is not a fixed value. So in other words, do not confuse 95% confidence with 95% probability. Those are two completely different things. Whether a confidence interval contains a population parameter depends solely on the value of the sample statistics. So any sample statistics that is in the tails of the sampling distribution will result in a confidence interval that does not include the population parameter. 1 minus alpha times 100% of all sample proportions will result in confidence intervals that contain the population proportion. These sample proportions that are not in the tail of the distribution in the figure will not result in the confidence interval that contain the population proportion. The value z sub alpha over 2 is called the critical value of the distribution. So it represents the number of standard deviations the sample statistics can be from the parameter and still result in an interval that includes a parameter. So table 1 shows some of the common critical values, but we're not going to use a table, we're going to use Excel. So Excel could give us a little more, actually a lot more than what they give us here. Notice that the higher levels of confidence correspond to a higher critical value. So remember, whenever we have a larger value, a larger confidence interval, the number is going to be larger because we're kind of guessing extreme values for Kim Kardashian's age. I think we said 20 and 60, something like that. So larger the confidence interval, larger the critical value over here. And now interpretation of a confidence interval. So at a 1 minus alpha times 100% confidence interval indicates that 1 minus alpha times 100% of all simple random samples of size n, the population whose parameter is unknown will result in the interval that contains a parameter. So a 90% level of confidence does not tell us that there is a 90% probability. We kind of already went over that part. The probability, there is a 90% probability the parameter lies between the lower and the upper bound. All right, now we get an example. All right, so when Gallup organization conducted the poll introducing the previous example, we got 45.1, and that's the value that we had here. Just multiply this by 100 and it will give you the percentage. 45.1% of the surveyed considered the amount of federal income tax they have to pay is too high. Gallup reported its survey methodology as follows. Results are based on a telephone interview with a random sample of 1,015 national adults aged 18 and older. For results based on the sample of national adults, one can say with 95% confidence that the maximum margin of error or sampling error is 4 percentage points. So determine and interpret the confidence interval for the proportion of Americans aged 18 and older who believe the amount of federal income tax they have to pay is too high. So here they didn't really tell us how they got this number. So let's figure out how they got the 4 percentage points here. So let's grab all the information that we know. So we know that N was equal to 1,015. We know that P hat is equal to 45.1% or 0.451, which we also have over here, but let's just write it down. The next thing that we're going to need is our confidence interval. They said with 95% confidence. And we could take this over here. So remember what we talked about earlier. We needed a, let's see. So the value of our z-score, if we have 95% of the data here, that means that we're sharing 5% with either side. So this side over here on the left is going to have a 2.5%. Over here, it's going to be same thing, 2.5%. And now we're going to look for this z value right here. So this is a z value of, if we have 2% here, or 0.02 plus 0.95, we're going to look at the critical value of z equaling 0.975. So again, we're looking at the area of these two right here. So we're looking for that area right there. And one more thing was our point estimate. E was equal to the z value, the critical value, times our standard deviation, which was the square root of p hat times 1 minus p hat divided by n. Okay, let's start with the z value. So we're looking for z of 0.975. And this is equal to, remember this here is a normal distribution. So normal distribution, do we need an area, or are we looking, or do we have an area? So here we have an area that we need that associated z-score for. So we're going to click on this one. Probability is our areas, so 0.975. The mean, because we're looking at the standard normal distribution, the mean is going to be 0, standard deviation 1, and hit enter. So this is our z value. So this, we're going to plug into this right here to get our point estimate. But before we do that, we have to figure out what the standard deviation is. Here, the standard deviation we said was the square root of p hat times 1 minus p hat divided by n. So this is equal to square root, so SQRT. And here we have a numerator and denominator, so I'm going to put parentheses for the numerator. And the numerator was p times, let's start parentheses for this inside part, 1 minus p hat, close parentheses for 1 minus p hat, close parentheses for the numerator, and we're dividing by the denominator, which is n. And here we just close parentheses for the whole square root. And this is our standard deviation. So now that we have this part here, we could find our margin of error. So remember, this is equal to z, our critical value times our standard deviation. So our critical value, z sub c, times our standard deviation. And there we go. That's actually, they did this a little bit off. Okay, well, theirs was a little bit off, but going off of what they said, just using those 4 percentage points, I'm guessing that they just added an extra percentage point because this is what they should have put. So the margin of error here was just this, and we'll see if it's still the same thing. So here they went out 4 percentage points. So what we're going to do is look at these two areas. So looking at that, we said that this middle portion was 45.1%, or you could think of this as 0.451. And what we're doing is we're adding and subtracting 4 percentage points. So when we subtract 4 percentage points, so remember 4% is 0.04. So this value right here is 0.451 minus 0.04, giving us 0.411. Over here, we're going to add 4 percentage points. So to this value here, we're going to add 0.04, giving us 0.491. Which if you look at the percentages, this is going to be 41.1%. This is over here is 49.1%. And that's all we do here. And let's see what they did. So they wrote it out this way. You could still keep it that way. I just wanted to write it out this way so you could see exactly what happened. So we're subtracting E over here, we're adding E over here. So subtracting it this way, adding it this way. So we have our percentage here, or our sample proportion here, and we're adding or subtracting 0.04 to the confidence interval. And there we go. So therefore, the lower bound of the confidence interval is 0.411. The upper bound of the confidence interval is 0.491. So again, we could say that we are 95% confident that the proportion of Americans aged 18 and older who believe that the amount of federal income tax they have to pay is too high is between 41.1% and 49.1%. And again, what we're doing is p hat minus our critical value z sub alpha over 2. And that's going to be for our lower bound and our standard deviation. And our upper bound is going to be p hat plus z sub alpha over 2 times our standard deviation, which is the square root of p times p hat times 1 minus p hat divided by n. So just to make it a little bit easier, we're adding and subtracting our margin of error, which is z sub alpha over 2, or our critical value here, and the square root of p hat times 1 minus p hat divided by n. So note it must be, yes, so we have to remember this part too. So it looks a little crazy, but this is just n times p hat times 1 minus p hat. That value should be greater than or equal to 10. If we have that, and if our population is, our sample size is less than 5% of the population, then we could construct an interval in this matter. So they did give us a margin of error like that. So the margin of error here is in a 1 minus alpha times 100% confidence interval for the population proportion. That's given by this value right here. So our critical value, the z sub alpha over 2, times our standard deviation, which is the square root of p hat times 1 minus p hat divided by n. All right, so from here, in the parent teen cell phone survey conducted by Princeton Survey Research Associates International, 800 randomly sampled 16 to 17-year-olds living in the United States were asked whether they have ever used their cell phone to text while driving. Of the 800 teenagers surveyed, 272 indicated that they text while driving. Obtain a 95% confidence interval for the proportion of 16 to 17-year-olds who text while driving. All right, let's grab this information. So 800 randomly sampled 16 to 18-year-olds. So we have n is equal to 800. United States were asked whether they have ever used their cell phones to text while driving. Of the 800, we have x equaling 272, indicated that they text while driving, obtaining 95% confidence interval. So with 95% confidence, find the population proportion of 16-year-olds, 16 to 17-year-olds in the United States who text while driving. All right, so let's start here. All right, so we have n equaling 800. We have x equaling 272. And we have our confidence at 95%. All right, so now that we have all of that, we could clear this out and kind of talk about what we're going to do. So again, the first thing that we need is from our line here, we need to figure out what p hat is. So our sample proportion. So p hat, we don't have like a formal p hat, so we're just going to use this here. P hat is going to be equal to x divided by n. Perfect, that's what p hat is. And just so we have it, 1 minus p hat. So 1 minus p hat is going to just be equal 1 minus p hat. And now that we have that, we have our population proportion. Now we need our margin of error. But in order to get our margin of error, we need our standard deviation. And our standard deviation. Remember, our standard deviation is equal to the square root of p hat times 1 minus p hat divided by n. Okay, so here we have the square root, SQRT. of here we have our numerator. So in our numerator, we have p hat times 1 minus p hat, and close the numerator divided by the denominator, which is just n, and close parentheses for entire square root. So this is a standard deviation here for this problem. The next thing that we need for our margin of error, remember our margin of error is equal to our critical value times our standard deviation for p hat. So standard deviation for p hat. Now that we have this part here, we just need to figure out what that z-score is. And let's draw a picture to illustrate what's happening. And here for this, we need a 95% confidence interval. So what we're saying is that we need 95% of the data to fall within that middle portion. So 95% is going to be 0.95, which means that we're sharing 5% with each of these sides right here. So half of 5% for the left, half of 5% for the right. So that's going to be half of 5% is 2.5%. So that's going to be 0.025 here and 0.025 over here as well. What we personally are looking for is this value right here. And we need that critical value, the z-score. So that z-score is going to take into account the area to the left of that, which is going to be the sum of those two values. So 0.025 plus 0.95, that gives us 0.975. So here the z-score for the area of 0.975, that's going to be equal to, remember this is a normal distribution. Is it a normal distribution or normal inverse? Normal distribution, do we need an area? Normal inverse, do we have an area? So here we have an area that we need the associated z-score for. So the probability in this case is going to be the area, so 0.975. Because we're looking at the standard normal distribution, we just need the standard z-score. We're looking at 0, a mean of 0, standard deviation of 1. And there we go. So this is our z-score. And now that we have that, we could construct our confidence, or at least find out what E is. So E is equal to our critical value times our standard deviation. So the critical value, the z-score, times our standard deviation, and that gives us E. So now that we have E, we could start constructing our confidence interval. So again, what we're looking at is this here in the middle, we have p hat, we have our sample, and we're looking for our population proportion. Our sample proportion will lead to our population proportion. And now we have to figure out what these boundaries are. So we have our lower bound, and we also have our upper bound. So for the lower bound, because we're going lower, we're subtracting our margin of error. So here lower is going to be equal to p hat minus our margin of error, this value here, and that gives us our lower bound. And now for our upper bound, because we're looking at a value higher, we're going to get p hat, and this time we're going to add our margin of error plus the margin of error here. And now we have these two values here. So what we say is that 0.307 is less than or equal to our population proportion, which is less than or equal to 0.3728, so 373. And there we go. That's our population proportion there. And let's see if we missed anything. So one thing that we forgot to do, and I'm always forgetting to do this, I'm really sorry, but we need to see if all this work, if we're able to use this form in order to find our confidence interval. So the first thing is we need n times p times, or p hat times 1 minus p hat. Whatever that value is should be greater than or equal to 10. So let's check that part out. So we have n, so equal to n times p hat times 1 minus p hat. And this value is definitely greater than 10. And the next thing we have to know is n less than or equal to 5% of the total population? So 800, is 800 less than 5% than the total population? Yes, because we're looking at all 16 to 17 year olds in the United States, and there's way more. It's safe to say that the sample size is considerably less than the population size. And now that we have checked that, we could continue on with the rest of this. So here they started with p hat and they checked this other stuff. So they looked at these values here. 179.52 is greater than or equal to 10. So we could continue on with that. So there are more than a million teenagers age 16 to 17 year olds in the United States. So our sample size is definitely less than 5% of the population. Because we want a 95% level of confidence, what we did is we looked at these values. So 0.02, this would actually give us a negative value here, but 0.02 would have given this value. And it's very close to what we got. We got something a little bit more exact. So substituting into formula 2 with n equaling 800, we obtain a lower and upper bound of the confidence interval. So the lower bound ends up being this value here because we subtracted our margin of error, and 0.307 is what we got here. Cool. And what about our upper bound? We added our margin of error, and we got 0.373 over here as well. And here the margin of error was 0.33. And step 5, this is what I believe is the most important part. So we are 95% confident that the proportion of 16 to 17 year olds who text while driving is between 0.307 and 0.373. And now using technology, pretty much the same thing. They go about it a different way with StatCrunch. But yeah, we were using Excel. So the effective level of confidence on the margin of error. So we stated earlier that the logic suggests that a higher level of confidence leads to a wider interval. So we could check the difference out. So for the problem of estimating the proportion of 16 to 17 year old teenagers who text while driving, determine the effect on margin of error by increasing the level of confidence from 95 to 99%. All right, so what we'll do is kind of leave these numbers here. So what we're doing is, we'll just write it out. All right, so with 95% level of confidence, we said that it's 0.307 less than or equal to our population proportion less than or equal to 0.373. And now what we're going to do is just change this from 95% level of confidence to 99% level of confidence. So 95 to 99. So p hat doesn't change. 1 minus p hat doesn't change. Our standard deviation doesn't change, but this here is what changes. So here we have the area of 0.975. Let's find out the new area. So with a 95% level of confidence, actually, let's do this in blue. So with a 95% level of confidence, we have 0.99 here in the middle. That means that the left and the right are sharing 1%. So we have 0.5% on either side. which gives us an area of 0.005. And same thing over here, 0.005. Adding those two together gives us 1%. Adding it to the 99% gives us 100%. So that's how we justify this area here. But now what we're looking at is this over here. So the z-score of this entire area, and that's going to be the z-score of 0.995. Actually, so what we could do instead of messing that part up, we could do this. So let's insert. And here for the z-score of 0.995, what we're going to have is equal to, this is a normal distribution. So not normal distribution, normal inverse, because we have an area that we need the associated z-score for. Probability in this case is going to be 0.995. Since we're looking at the standard normal deviation, the standard or the mean is going to be 0. Standard deviation is going to be 1. And there we go. So now for the margin of error, remember the margin of error is the standard deviation times our critical value. So our critical value times our standard deviation, which is this value here. Perfect. And now going down this way, let's clear this out. Going down this way, we have p hat plus or p hat minus our margin of error, p hat plus our margin of error. So equal to p hat minus our margin of error, because we need a lower number for the lower bound, and equal to p hat plus our margin of error. There we go. So now looking at these values here, let's put it all on one number line so that we could see exactly what's going on. So here, what we're looking at here in the very, very middle is p hat. So we have 0.34 and starting off with 95% level of confidence. So with 95% level of confidence, what we have is 0.307. So we went out this way, 0.307. Let's get a different color. So 0.307 here. And we went out this way as well, 0.373. So we have those values there. This makes up our 95% level of confidence. And for our 99% level of confidence, we went further out to the left. We went 0.2968, so 297 here. And we went out this way, 0.383. So here we have our 99% level of confidence. And there we go. So these numbers do make sense. So the larger the confidence interval, the larger the confidence, the larger the interval. The smaller the confidence, the smaller the interval. If you wanted to go out for 75%, you guys could, but it would be a little bit shorter here and here. Doesn't really seem realistic, but kind of does make sense. Now let's see if we missed anything. So by hand, they computed these values. They found our margin of error to be 0.04. Remember earlier, it was 0.33. So 0.33, 0.43 on this one. And here they used the TI-84 calculator. We used Excel because it looks cooler. And they got the midpoint here from the two. Still kind of cool. Just so you know, the midpoint is just what p hat is, and they're just talking about the midpoint of the area. So the midpoint of the confidence interval is just going to be p hat because you go out the same distance to the left and to the right. And here, the margin of error for a 95% confidence interval found in the previous example was 0.33. So increasing the level of confidence increases the margin of error, resulting in a wider confidence interval. And now the effect of sample size and the margin of error. So we know that the larger sample size produces more precise estimates, aka the law of large numbers. So given that the margin of error, remember it's this value right here, our critical value times our standard deviation. And the standard deviation in this case is being divided by n. So the square root of p hat times 1 minus p hat divided by n. So the larger the number here, the smaller the value is. So just think of like our numbers. So if we have 1 over 1, that's equal to 1. 1 over 2 is 1/2. 1 over 4 is 1/4. 1 over 100 is a lot smaller. So it starts getting smaller, the value starts getting smaller and smaller and smaller, the larger the denominator is. So we can see that increasing the sample size n decreases the standard error. So the margin of error decreases. So the smaller the standard deviation, or the larger n, smaller standard deviation, smaller margin of error. So this means that the larger sample sizes will result in a narrow confidence interval. Next, determine the sample size necessary for estimating the population proportion within a specified margin of error. And here we're going to use this equation. So this is n is equal to p hat. I know it looks a little crazy right here. N is equal to p hat times 1 minus p hat times our critical z-score divided by our margin of error, and those two values are squared. Problem, the formula uses p hat, which depends on n, so the quantity we are trying to determine. So again, remember we talked about any information is good information. 1 minus p hat, critical value over e squared. Okay, so here we need to find out what p hat is before we could even figure out what the sample size is, right? So what do we do? So if you kind of grab your calculator and start looking at all the different ways that we can multiply numbers, if we multiply 0.1 times its complement, so remember this is just the complement, right? So 0.1 times 0.9, that gives us 0.09. 0.2 times 0.8, that gives us 0.064 or 0.16. And we could continuously multiply these numbers, or that might not even be true, but we could continuously multiply those numbers, but the product that will give us the most amount in general is going to be a p hat equaling 0.5. So 0.5 times 0.5, that gives us 0.25. So multiplying those two numbers is going to give us the largest amount possible. So whenever we don't have a previous estimate, we're just going to use 0.5. So now 2 possible solutions. So use an estimate of p hat based on a pilot study or an earlier study. So p hat equaling 0.5. P hat, otherwise use p hat equaling 0.5, which gives the largest possible value for n for a given level of confidence and a given margin of error. So in this case, whenever we have these values here, so round to the next integer, where p hat is a prior estimate. So we're always going to round to the next integer, so that way we could, because we always need that value, and I'll explain it a little bit once we get those. So if a prior estimate is unavailable, we're just going to have this, but we could still just use a previous equation. All right, an economist wants to know if the proportion of the US population who commutes to work via carpooling is on the rise. What size sample should be obtained if the economist wants to estimate within 2 percentage points of the true proportion with 90% confidence? All right, so Again, what we're looking at is not E. We're looking at N equaling P hat times 1 minus P hat times our value, our critical value divided by E, and we're squaring these values. So the things that we need right now is P hat and our Z value, which we could get from our confidence interval, and we need to figure out what E is. E in this case, let's read everything again. So economist wants to know if the proportion of US population who commutes to work via carpooling is on the rise. What size sample should be obtained? So that's what N is. If the economist wants to estimate within 2 percentage points, so 2 percentage points of the true proportion with a 90% confidence. So here we could get this value with 90% confidence. Ooh, they didn't give us anything for P hat. So first I'm gonna guess A, the economist uses the previous estimate, 10%, or if they don't have anything. So looking at this part, we have P hat equaling 10%. And now that we have this data, we could come over here and fix everything. All right. So we have P hat. So P hat we said was 10%. 10% is 0.10. Our Z value, we don't know. We have our margin of error, which is 2%, and 2% is 0.02. And lastly, we're going to look at our Z score, so our critical value, our Z sub C. So our critical value, we need 90% confidence. So let's draw a picture illustrating that. 90% here in the middle, or 0.9% here, which means these two are sharing 5%, which means, or I'm sorry, they're sharing 10%, which means that 5% for either side. So 0.05 here, 0.05 over here. So that means that this value over here is going to be Z sub 0.95. So remember, this is a normal distribution. So we're going to hit equals normal distribution or normal inverse. Do we need an area or do we have an area? In this case, we have the area that we're going to need the associated Z-score for. And our Z value, or our percentage or probability, is 0.95. Because we're looking at the standard normal distribution, it's going to be 0 for the mean, standard deviation of 1. Hit equals, and now we have this value here. So now that we have P hat, good, 1 minus P hat, almost. Our critical value, Z sub C, awesome. E, we have E, and we would just square those values. So just to make it a little bit easier on ourselves, let's get this and do a 1 minus P hat. So this is equal to 1 minus this value right here. And now that we have all of that, we can figure out what N is. N is equal to P hat times 1 minus P hat times, we're going to do parentheses because we're dividing these two values. Z sub C is this value, and we're dividing E. And now that we have this in parentheses, when we square it, it's going to square everything inside those parentheses. So square raised to the power 2. And this is what we have. So now what we're going to say is we need a sample size of 608. No, we need a 609. So again, it doesn't matter what the value is over here. Even if we have 1 or 0.1 somewhere over here, Even if we have a value, we would still need that 0.1 of a person in order to make this a complete sample size. So we're always going to bump this value up one. So instead of 608, we're going to use 609 for that sample size. And let's see if we missed anything. So here they got the z-score 1.645, which is similar to what we had over here, a little bit more accurate. So round this value up to 0 to 609. So the economist must survey 609 randomly selected residents of the United States. B, the economist does not use any prior estimates. So if he doesn't have any prior estimates, that means that this is going to change right here. So instead of this being 0.1, this is going to be 0.5. And that changes p hat. It changes 1 minus p hat. Doesn't change any of this, but it does change our sample size. So without a prior estimate for the sample proportion, the economist needs a sample size of 1,691. Again, we're going up one more. Doesn't matter that this value right here was a 9. What matters is that we had an extra person right here, or part of a person that we needed. All right, so take a look at how extreme those values are. So we need a sample size of 600 versus a sample size of 1,600, close to 1,700. So some information, this is a really great example of when I say that some information is good information. We still needed some information to figure out what this value was. And it helped us out a lot with trying to figure out what the values ended up being over here. So the value over here of 1,600, close to 1,700 versus 600. So over 1,000 more without any prior information. So 1,691.3 rounded up to, what is theirs different? If we cut this off. So 1.64. Okay, well, that's what we ended up getting here. It makes things a little bit crazier. Well, they kind of cut things off a little bit. What did they use? 645. 1.645. Oh, okay, there we go. So again, we were a little bit more accurate with our estimate instead of theirs. But anyway, so they still had to round up one. So they ended up with 1692 instead of 1691. So the effect of not having a prior estimate of P is the sample size more than doubled. So close to triple, the sample size nearly tripled. Yeah, so there we go. And that wraps up section 9.1. If you guys have any questions, don't forget to email me. But if not, good luck. Bye.